Hello everyone, I am Hafizur Rahman, a PhD student of Guangzhou University, China. I am going to present my paper. The title of my paper is Trustworthy Data Acquisition and Faulty Sensor Detection Using Gray Code in Cyber Physical System. My presentation consists of three parts. In the first section, I will generally introduce cyber physical system and their application. Then I will discuss the importance of trustworthy data acquisition in cyber physical system and IoT environment. I will discuss different problems faced by the IoT system. Then I will discuss our proposed framework for trustworthy data acquisition and faulty sensor identification. I will conclude my presentation with some remarks. So what is a cyber physical system? Generally, a cyber physical system integrates physical devices such as different sensors with the cyber component to form a scenario integrated analytical system that may respond intelligently to the dynamic changes of the real-world situation. Nowadays, millions of embedded devices are used in different domains such as health, agriculture, education, industrial application, supply chain, structural health monitoring, weather forecasting, military observation, and so on. Generally, in IoT, our cyber physical system consists of three layers, such as physical perception layer, network layer, and application layer. In physical perception layer, the interconnected things such as sensor or mobile devices, they monitor and collect different types of environmental events. These data can be further aggregated, fused, or processed and analyzed in order to extract some useful information at the fog server or cloud server to enable intelligent services. No matter how the diverse in IoT environment are, they always follow the 5 basic steps, such as sense, transmit, store, and analyze the data. Finally, they act accordingly to the environmental event. Furthermore, most of the IoT systems operate in a dynamic environment which need immediate action without waiting for a test report from the entities. Whenever some event occurs, they need an immediate action, a quick response without the need to take response from the cloud server. However, due to the technology limitation and environmental influence, such as sometimes we have equipment fault, noise, or some security attack, so the sensor data collected by these physical devices or the IoT devices is inherently noisy and they may trigger many false alarms. These false or misleading data can lead to wrong decision too. Therefore, it is highly desirable to acquire and share meaningful information or data from a large volume of noisy data. However, the reliability of the data, such as trustworthiness, depend upon at least three factors, such as the data is free from error, they need to up-to-date and originate from trusted sources. But especially in heterogeneous and complex IoT environment, it is a difficult problem, and it is hard to identify or differentiate a fault, nice cyber attack, and real-world fact from each other. And here can be a question too. What will be the situation if we collect, if we receive, or if we acquire low quality, untrustworthy, or compromised data, and during the acquisition time we apply different strong algorithm or security protocol to process, store, and transmit the data and we have decision for various cyber physical application. So the decision made in the cyber system based on the collected data may be meaningless, or sometimes it will be untrustworthy, such as we may process the compromised data, we may transmit the compromised data, or even we may encrypt or store the compromised data. So therefore, we need such a system, we need a trustworthy data for cyber system before to invest our time and cost for processing, storing, and transmitting the unsecure or untrustworthy data. In the literature, we have any solution for this problem. Currently, we have no comprehensive approach to the problem of high data trustworthiness, such as the data is originated from a trusted source, up-to-date and free from error. Current approaches for measuring the data trustworthiness are generally meant for web and traditional sensor network. As we know, the traditional sensor network and web domain, they are totally different from IoT environment because we have different scenario in IoT as compared to sensor network. Some of the researchers consider security and privacy before the data processing, storing and transmitting. However, for complete data trustworthiness, we require an articulate solution by combining different approaches and techniques. In this work, we perform a network generalized trustworthy data collection framework for trustworthy data acquisition and file sensor in the IoT environment, such as at sensor node level. During collection time, a sensor module can decide in real time whether the acquired or sensed data is trustworthy or not. If it is trustworthy, it will forward to the upstream node, such as the gateway. Once the gateway collects the acquired data, they also decide that the collected data or the acquired data is trustworthy or not. Once it okay, then forward it to the fork server, a cloud server. The key idea of this framework, it allows a sensor module to verify whether or not the acquired data before transmitting to the upstream node, it is trustworthy or not. It also identifies whether the received data is trustworthy or not before aggregating at the gateway. Furthermore, this framework also facilitates to identify a faulty sensor too. For reliable event detection in real time without waiting for a trust report from the end entity, we use collaboration between the IoT devices and we use gate level modeling with the Verilog user-defined UDP to make sure that the collected or event information is reliable before sending to the end entities. We use gray code technique in gate level modeling as a flag, which IGTDC framework can be implemented or deployed at the sensor module level. We envision that IGTDC give online and network low-cost energy efficient due to reduced circuit switching and power consumption. Later we will see it. Furthermore, IGTDC is based on simple Boolean expression, sum of product and sum of sum. Through IGTDC, a simple Boolean expression can be transformed in accordance with the type of the IoT application. Therefore, here you can see some of the Boolean function, which is we call Boolean gate. Therefore, IGTDC can operate in any heterogeneous IoT environment or a particular IoT application, such as fire detection. That's why we call this framework generalized trustworthy collection framework, because IGTDC is adaptable, operate at the edge of the network, i.e. IoT sensor module, and can utilize for different IoT applications. Furthermore, here if we explore more, the sensor module are object domain or central processing unit are deployed according to an engineering driven deploy method to cover a particular area of interest, such as fire detection, smart irrigation system, and so on. For simplicity, here we consider the fire detection, and the design prototype of fire detection sensor module are installed in 3 different locations. Here we call object domain 1, object domain 2, okay, object domain 3. Inside of the sensor processing module, we have three different sensors such as temperature sensor, smoke sensor, and humidity sensor. So these three sensors are available in each object domain 1, 2, and 3. Here we are just exploring one object domain. Okay, so whenever some event occur, so at the same time we are considering the data from the three different sensors, which is humidity sensor, smoke sensor, and temperature sensor. Once they collect the data are come to comparator. Okay, for each sensor we have different comparator. Once the data collected and they pass the threshold, okay, so they come to the Boolean gate. By using the Boolean operation and the collaborative IoT manner, we apply different logic based on the data. Here, for example, we can see logic table. Okay, suppose in the first scenario 0 0 0, it means there is no event. Okay, temperature is 0, smoke is 0, humidity is 0, so no data is observed. Okay, so the output is also 0. In the second scenario 0 0 1, okay, here temperature is 0, smoke is 0, humidity is 1. Okay, so the output is also 0. So we put some scenario. Here total 8 scenarios are available, but out of 8 only 4 output are generated based on the Boolean function. Okay. At the same time the output is generated. Here we can see y2 and y. Okay, one is for the gray flag. Later we will see the function of the gray flag. So through collaboration among the sensor, whether user-defined UDP, a large amount of sensor data is filtered clean, and only reliable data is forwarded to the gateway sinks. For example, the output is considered reliable if and only if. This is the main condition. If n are n minus n sensor such as temperature, smoke, and humidity. Here n is 3. For example, if 3 are 3 minus 1 mean 2. Out of 2 sensor detect environmental event and the sensor exceed the threshold value at a given time interval, it will be reliable. Otherwise, it will be considered faulty or fake compromised sensor. As a summary, using the logic output value, a sensor module, which is this one, okay, it can decide locally without waiting for a trust report of the fork server or gateway or cloud whether the raw data is reliable or not. If it is reliable, then it will be routed toward the gateway for further data aggregation along with the gray code as a flag. Okay, as a flag for data aggregation and faulty compromise or faulty sensor detection. So now we are coming why we are using gray flag in our proposed framework as a trust aggregation technique which can be used for faulty compromise sensor detection too. Gray code is a single coding method commonly used in digital conversation. It is defined as follows: GI is equal to BI exclusive R BI plus 1, where I is equal to 0 till n minus 1 and B is just Bn minus 1 up to B1 B0. Furthermore, as we can see in the example, a binary code conversion over 4-bit binary stream of bits. For example, B1, B2, B3, B4. Corresponding gray code can be, for example, 1110. If we have data like this, so the corresponding gray code for this particular bit of string is 1001. A gray code is a reflected binding code, as we mentioned before, which you can call cyclic code or minimum error code or single step code. Applications of gray code have been found in many different areas, including digital circuit design, digital communication system, and image processing. Furthermore, it also commonly used in error detection in some TV cable stream or system, especially it is used in high-speed decode circuit to reduce the circuit switching and digital communication, where analog information is converted into digital and vice versa. For example, it reduces circuit switching. How? Here we can see 11110. If we see the corresponding output, so here only one bit is different. The rest of them are same. Okay, so the final, here we can see the final result. For example, 1111001. If we see the output, so the output stream is only different by a one single bit. The rest of them is same. Okay, 111000. So here we can see 1100. If we see the another example, 1010, here we can see 11. Okay, and so on. In our scheme, we use gray code as a secure trust aggregation technique, which can be used for faulty compromise sensor detection too. It helps the gateway to investigate and identify a faulty compromise sensor using backtrack technique. Moreover, in order to preserve the confidentiality of the data being transmitted by sensor module, gray code sequence is introduced with the output sensor module as a flag to overcome the suspicions introduced by cryptography. It will help the gateway in a secure way, such as which sensor participate or observe the event and vice versa. If any adversary wants to know the status of a particular sensor, it is not possible to directly trace or compromise the sensor. It is not even if a particular sensor become compromised, faulty, or did not participate, the gateway can easily identify and figure out. For instance, 3 out of sensor of logic of domain 1 to observe an event, while 2 out of the 3 sensors observe the same event at the same time. As a result, all the sensor module will forward the output along with the gray code to the gateway. The final decision will take by the gateway for a reliable event. Furthermore, using backtrace of gray code, a gateway can also find out a faulty or compromised sensor and can resolve the conflict with other multiple noisy and like other traditional approaches such as truth discovery, data provenance, signal correlation, and so on. Here I will give one example. When a sensor reading is ready to be transferred from an IoT sensor, it first goes to the sensor module. The K-map output are either 1 or 0 that is being given. K-map is just a truth table representation of truth table. We combine the trustworthiness and those attributes to evaluate the final confidence in the raw data itself. As shown in the figure, using Verilog simulation, we zoom this. We run the simulation for 250 seconds. According to the logic object module for file detection, 4 out of 8 output values are routed to the gateway, represented by one output column with the corresponding flag in the table. The output will be routed to the gateway if and only if our sensor, at least two sensors such as temperature, smoke and humidity, detect the environment elements such as fire. As shown here, for reliable event detection, we can see that out of 3, only 2 reliable events are detected at 60 seconds and 180 second and a 250 second simulation period for fire detection. Here, for example, in temperature, we can see one value here, but that did not appear in the output signal. Okay, here in 180 or 160 humidity sensor, we detect a faulty or compromised signal. It may be any of them, but in the output signal it not appear. In the same way, in another type of simulation, this figure displays temperature smoke sensor having faulty or partially altered signal at 700 seconds and 300 seconds respectively, and 900 second simulation period of time for fire detection. In V, they have no faulty or altered signal injection. This implies that the collected data is reliable and the corresponding event signal is trustworthy. Here, in another case, a unique faulty or compromised signal is inserted during the simulation time. For the humidity sensor, the corresponding event signal is recorded at 300 seconds, whenever the gateway collects such data, it can drop the data from the aggregation, or the data recognition method can be applied for reliable data. Moreover, by using the gray flag, the corresponding faulty or compromised sensor can be backtraced as well. So, as a concluding words, we need trustworthy data for trustworthy cyber physical system before to invest our time and cost for processing, storing, transmitting of unsecure data. We need to identify the acquired data is trustworthy or not. Finally, once we sure, we need to transmit the trustworthy data to the upstream node. Before aggregation, we also need to identify that the acquired data is trustworthy or not. In the literature, we have several techniques available. So, once we use different techniques, we can achieve data trustworthiness. In this work, we built a tiny utility using PLD. It works at the edge level, such as sensor module level, and other two data trustworthiness in the using collaboration among IoT devices. So, by using this technique, we can achieve data trustworthiness as well as we can also identify if we have any fault in the sensor. Thank you. Thanks for your time. If you have any question, you can directly ask me or you can send me an email.